Hello everybody on this beautiful summer day. Today I am going to be talking about science and the scientific method. I am not going to be talking about the four basic divisions of science, which are applied science, formal science, which really isn't science, it's kind of just like the language we use, social sciences or natural sciences. That's not what this is about, although I am going to be using the scientific method generally drawn on by natural science. And it's also not a talk about scientific disciplines or anything like that. I am going to throw a lot of definitions at you. I will try not to read them verbatim. I've actually wanted to do this video for a while. I just had to get my thoughts together and get some slides together and figure out the best way, I think, to do this, because there is a lot of misconceptions about what science is and about what the scientific method is, and a lot of it is deliberate confusion by certain groups of people, and I'm not going to go into that. That's a talk for another time. But a lot of it's just misunderstanding, because a lot of people just aren't geared towards science, and that's fine. So I'm going to explain it to you. And you can use the scientific method in other applications. You don't just need to use it to try to, apply it to an existing theory or hypothesis or whatever. Before I can talk about the scientific method, I need to define what science is. And this is the definition that I could best think of. These definitions are my own, derived from other working definitions. And as you can see here, what's real important about this is that science is a method, all right? It's a descriptive process. It does not prove anything. Proofs are for philosophy and math. We never really prove anything in science. We just eliminate things that have been falsified. Like, we disprove things, if you will. Somebody puts forth a hypothesis or an idea, and it's tested and it's found out to be false. It's rejected and we move on. So I just needed to clear that up first. In these definitions, you're going to see some yellow words. Those will be defined later. That's because these things are all kind of tied into one another. But here I'm going to define for you the scientific method, and I am going to read it verbatim. It's a systematic procedure consisting of experimentation, observations, collections of facts and data in order to form, test, modify, or falsify a hypothesis. Falsify is also a synonym of refute. It is not a rigid process and may vary slightly depending on its application. So here's the definition of falsibility or falsify or refute, if you will. And as you can see, you have to use the scientific method to falsify a scientific concept. You can't just randomly grab something out of the air and say, yeah, I falsified it. Like, you can't sit there and say, the theory of gravity is incorrect because I don't think it is because I see a balloon rise in the air. You've just made a statement. You haven't proven anything. You haven't falsified anything. You're just talking out of your hindquarters. Now, if you develop a method to show that the theory of gravity is incorrect, that's one thing. But just the blanket statements like that don't mean anything. And you can't refute scientific concepts with philosophy. I know science came from philosophy. Things change, things adapt. Science and philosophy have kind of split. They're still somewhat connected, but not like they used to be. Like, I cannot sit here and explain the natural world by just pointing to my head and in my head saying, well, if A does B, then B must be C, this must be D, which must be E, which equals F, because I thought of that process in my head. That's not science. That's fine for philosophy, and it has its place, but it does not have a place in the scientific method. What are the steps to the scientific method, if you will? Well, it's not very rigid, like I said, but this is a general guide. You can either start with a question here, and here's the definition of a question as well, just so you know what it is, because the scientific question is blue butterfly is awesome. The scientific question is different than just an average question, all right? Or you can start with an observation, which the definition for an observation is here. Now, your observation, these two are kind of interchangeable, if you will. Like, a question could lead to an observation could lead to a question. For example, I could sit there and say, I can observe that the sky is blue. Well, clouds are starting to move in, but the sky is blue on this lunchtime break. That's my observation. And my question could be, why is the sky blue? Or I could be inside thinking, wonder what color the sky is right now. And then I walk outside and observe and see what it is. I could do that as well. See, so they're kind of interchangeable and they kind of go back and forth. But the point is these two are key because no matter what order these two come in, they're going to be used to form your hypothesis. Okay, now your hypothesis is the first real step to the scientific method after your initial observation or question. Here's the definition of what a hypothesis is. Now, I'm going to read this to you verbatim because I think it's important. A hypothesis is a limited concept or idea that is meant to explain some phenomenon that is testable through experimentation and or observation that will lead to further investigation. Any further investigation will either support or refute your hypothesis. That's key. You're going to collect more data, if you will. All right, and here's the definition for data, because this is important. All right, you're going to look for evidence, if you will. Did he land on my nose? No. You're going to look for something called empirical evidence. That is not the same thing as just kind of like evidence we would say in everyday speaking. We're going to run into this. Scientific definitions tend to be a little different than everyday lay speak, and that's fine. I mean, we're all in careers or professions where one word does not mean what it means in everyday talk. It's used to mean something else, and that's fine as long as it's defined, and that's what I'm doing here. Now, the thing with empirical evidence is that, or just evidence, is it's a very complex subject, and I could do a whole video on that, but I'm not going to do that here today. I'm just showing you the definition of what it is. Okay, now, why do I say experimentation, which is the definition here, versus observation? Why can I use one or the either in the process? Because I already did an initial observation, so why would I do more? Well, because you can't always run an experiment. All right, experiments are under controlled conditions, and as a part of an experiment, you need to have what we call a control. Now, controls are very important because they kind of remove the bias from your experiment, but your experiment has to be relevant to your initial question in forming your hypothesis, okay? It can't be something totally irrelevant or off base that has nothing to do with any of it. And hypotheses are more targeted. Your questions are more targeted in science than they are in general. Like a bad hypothesis would be, what's the meaning of life? Where do you even begin with something like that? I mean, that's not a targeted good question, all right? So, but anyway, back to experiments. So you have your control, and you can run one or more experiments in order to falsify or support your hypothesis. Now, you also need to remember that when running your experiments, you need to know the limitations of your equipment, because that's part of the observation thing, okay? You may have a good, solid hypothesis, but for whatever reason, you can't test it because your equipment's not sensitive enough, or you don't have the availability of the equipment, and that's fine. What will happen is if you don't have sensitive enough equipment, you may have huge margins of error or standard deviation, and you can't really falsify or support your hypothesis. You're just going to end up with a big question mark. So you can nip that one in the bud before you even get started, okay? And observation. Why is observation listed? Because not all, like I said, not all science can have experiments. And so observations can be key as well, like in geology. Key observation is something we call strike and dip. And if you got a bed like this, we use an instrument called a Brunton compass, which I've gone through in videos before. You place it down, you take your measurement, your strike and dip, which is the attitude of that rock in present space and time, which you need to document the location as accurately as you can, and take pictures if you can so other people can find it and verify or falsify it in the future. So now say I've taken that measurement on that bed right there, and I go a kilometer away and I see strata that looks exactly the same to me, and I take that strike and dip. Now, those are observations someone else can either verify or falsify, and I'm going to come back to those when we get into the predictive part of this, okay? So observations can be used in lieu of experiments, but either way, you're still collecting data, you're still collecting facts. Now, it's key here to remember facts, A fact is just a tidbit of verified information. That's all it is. It has nothing to do with hypothesis versus theory or anything like that. Facts are not above theories. That's not what it is. A fact is just a piece of information. Okay. Now, I have noticed that some scientists have sat there and said, when talking about theories to people who don't really know the difference, and I ain't going to touch on a theory, but I'm going to save that to the end. They've often said things like, well, theory is a fact, but they're using the fact like someone would use it in everyday speak. All right. And that's a language thing that we as scientists need to work on. All right. But a fact is not above a theory. Okay. It's not above a hypothesis. It's not anything, because hypotheses and theories are descriptive in nature. All right. A fact is a bit of information. It doesn't predict. It doesn't describe anything. It's just a fact. Okay. So you've got your experiment, your observation, you're starting to assemble your data, your facts, your evidence. There is a difference between an experiment and a demonstration. This is the definition of a demonstration. A lot of times, even as scientists, we will use the terms interchangeably, but they do not mean the same thing. You don't need a control for a demonstration. A demonstration is just a way of showing a unrefuted bit of information, how that would work. You know, it's an explanation, essentially, is all it is. Okay, so you've got all this stuff together, and now you're going to do the analysis part of the scientific method. Now, when you do conduct an analysis, it's just comparing the results, comparing your information against something. You may generate a graph, and say you get a nice graph like this, all right? And your points all point really close to that. You have low standard deviation, all that stuff. That may be where you stop. You may have gotten your information there. The scientific method does not always lead to a theory. I'm going to get into that in a little bit. But it's just a way of analyzing all this stuff you've collected. You may develop a model. And this is the scientific definition of model. I am going to read this one as well. A systematic description or illustration of an object or phenomenon that has the characteristics of that said object or phenomenon. They can be visual, mathematical, or material, often used to aid in the prediction set forth by a hypothesis. They can be used to demonstrate well-established concepts as well as modify existing concepts when coupled with new data. Most models are not intended to be 100% reflective of reality. Visual and material models do not have to be to scale. So what does that mean? Well, a lot of people, when they think of models, they think of the models you buy in a hobby store, the ones that are scaled down to a specific ratio and actually as accurate as they can possibly be at that scale. That's not necessary. Like if I'm trying to show you, say, the rotation rate of the Earth during a specific phase of the moon or something, and I'm just showing you the phase of the moon, say at that particular time from the Earth, and I have a light over here, my globe here, which doesn't need to be to scale relative to the moon, because I'm just trying to show you something. Okay, I'm just trying to show you if I stood here, I would see that moon at that phase. I do not need to build a 2-scale model of the Earth, Moon, Sun system. I don't need to do that, all right? And this is something a lot of people don't understand, because I'm just trying to show you one aspect of that system. I'm not describing the entire system to you since the beginning of time. Now, in the definition that I just gave you, the word prediction came up. And predictions are very important. Here's the definition of a scientific prediction. Now, it's key that you need to make accurate and precise predictions, all right? Like an accurate and precise prediction of something would be, take that strike and dip thing I was talking about earlier and say I have my strike and dip on this bed, the outcrop over here in a kilometer away, I've got the strike and dip over here on what I suspect is the same bed over here. Now I can extrapolate my prediction that if I'm about to come down to the halfway point between the two, at depth X, I should hit the top of that bed. That's a good prediction. And if somebody drills down there and they hit it, I've made an accurate and precise prediction. Now, I've done a video on accuracy versus precision before. I'll link it below. What is not a prediction is also known as what we call prophecy. All right? Like, this is not a prediction. at some time in the future, while human beings are still alive, a lot of people will die. Yeah, who cares? What is that? While human beings are still around. So basically that's any time from you made that statement till human beings are gone. You said from now into the future. That's from now until the end of time. And a lot of people will die. Well, how many is a lot? Where? You gave very little information. And you can kind of tell the difference between a prophecy and an actual scientific prediction, because prophecies never really they never come to fruition because they're so vague in their construct to begin with. They never make predictions, they make post-dictions. Right? Like if you take Nostradamus, for example. No one has ever accurately predicted anything he has ever said using his quatrains. All right. It's not until after something happens that people go back and go, oh yeah, let's fit that square peg into that round hole the best we can. That's not how it works. And if someone has made, and I'm going to get into how you can kind of use the scientific method to falsify the supernatural, because science doesn't deal with the supernatural. All right, I'm going to get into that in a little later. But you kind of can use it to falsify. Like if someone is claiming, like if they take something like Nostradamus or something, and they sit there and they do give based on whatever babble and whatever quatrain that on this specific date and time the world's going to end, all humans are going to die, and then they give a specific date and time. That time comes and passes. We're all still here. No one noticed. Okay, so that guy goes back and sits there and does it again. Okay, now I've redone it. It's this date time. Same thing. Passes, nothing. And he does the third time, the fourth, and the fifth, and we're all still here. It's safe to say 100% you've falsified that guy's claims. You can ignore him. He has nothing to contribute to the scientific method or process or anything, because he has falsified his own stuff repeatedly and he keeps doing it. All right, so it's just something you need to look out for. So I want to touch on this. Well, science describes the natural world and doesn't deal with the supernatural. It doesn't. Like you see the sky behind me here? Like I could come up with a hypothesis sitting there saying, well, maybe the sky looks blue to me because it has to do with the wavelengths of the light reaching my eyes being filtered from the atmosphere. I can test that. That's testable. Okay, I can test that hypothesis. Now, if my hypothesis is dragon giants from a different dimension who are invisible reach through their dimension at every dawn and paint it up there, I have no way of testing that. That's garbage. All right. From a scientific standpoint, I can just not. It falsifies itself in the fact that it's not testable. It's done. It's gone. All right. Now, some claims are a little more ambiguous, and I've done this. I'm going to link the video below. I'm going to use this example here. The claim of this guy was that there's a giant's footprint in granite. Well, I ask you to watch that video because I just go through the geologic aspect of this and I tear them apart from that, but you can attack this from a biological standpoint as well. Is his premise testable? This is a giant's footprint in granite. Yes, I can go up there, I can see it. And the short answer is it's not. And I can sit there and describe, well, I can gauge by the size of the footprint using the human frame, because that's part of his claim that it's human. I can get a height, and I can sit there and try to extrapolate with our physiology is say it comes out to be 30 feet tall or 10 meters. Can a human being even live if they're that tall? But in the video, I just attack it from a geological aspect because you cannot. I falsified his claim that that's a giant's footprint in granite. So some supernatural claims are a little more ambiguous, but they can be falsified. So now you've done your analysis, and now you have to form a conclusion. And it's just a summary statement of your hypothesis that either supports it or refutes it. And if it refutes it, you go back to the drawing board. All right, you start re-asking more questions, more observations, and reformulate. Your hypothesis may in entirety be falsified, or in part. Like, for whatever reason, the general gist of the hypothesis was okay, but you need to go refine it. That's fine, you can do that. but you get your conclusions together and you make a statement. And this is where science, in my opinion, as a scientist, fails people a little bit. We tend to, like most people, report our successes and ignore our failures. I, for one, am notorious for posting my failures on YouTube and other platforms, and my observations, demonstrations, and experiments. And I wish more people would really do that, because being wrong is just as important as being right. Being wrong doesn't make you stupid. It doesn't make you ignorant. It just means you're right. Something's right, but in a different direction. And that's fine. And, we are human beings, even scientists. So we like to celebrate our successes and kind of brush off our failures. But failing is part of learning. And you tend to learn more when you fail. But anyway, that's a rant for another time. Okay, so now you've got your conclusions, and you may derive a scientific law from your conclusions. This is the definition of a scientific law. Now, as you look at this definition, I'm not going to read this one verbatim to you. You can see that in this definition allows for the ability for laws to transcend theories or hypotheses, and that's what they do. I mean, the laws of physics apply to chemistry, geology, astronomy, cosmology. They apply everywhere. All right, so they can transcend hypotheses and ideas. They aren't above them either. Okay, that just like a fact isn't above a scientific theory, scientific law is not above scientific theory. Okay, so you've got your conclusions, you've found nothing to refute your hypothesis, you've come up with a nice scientific law or something to that general effect. And so now what do? You can stop right there. You don't need to go any further. If you've answered your question, your initial question, you can stop there. And that's actually what most of us do. Theories are so well established that we tend to work within them, one or more at a time. So we'll form hypotheses commonly, but we tend to stop at that conclusion. Although we could ask further questions, like if it's new ground no one's gone to before. So now you've come to the point, say you haven't answered all your questions, so you come up with further questions. You're breaking new ground. You're treading where no one's treaded before. So you're going to eventually develop a scientific theory, something new. So something where no one's been before. So this is a scientific theory. It's a well-supported explanation of some aspect of the natural world based on a body of knowledge that has been repeatedly confirmed through observation and experimentation, despite all attempts to falsify it through the scientific method. It is the best working explanation, notice I said it's an explanation, of some phenomenon using the currently available evidence, and it can be modified to fit new data. It is not a guess. All right? It does not mean anything that it means in lay speak. All right? And scientific theories explain things, unlike facts, which are just bits of information. So that is the definition of a scientific theory. And if you get to that point, you will have somebody is going to come along and try to falsify, because like a hypothesis, a theory can be falsified. And have theories been falsified in the past? Yes, they have. Now, an example of this in geology would be what was called Neptunism back in the 19th century, the concept that rocks were deposited, precipitated from seawater, all rocks, granite, sand, so it didn't matter. Well, that has been a falsified theory, if you will. And we know that doesn't happen. And then there's stuff that's not really, theories that aren't really falsified, but they change, because that's what science does. It changes to fit the data, all right? It doesn't change the data to fit its concept, all right? If somebody's doing that, they're not doing science. Despite what they claim, they're not doing it. So theories can change. Then you get things that are hypotheses that never become theories, or or they get falsified, but they lead to a similar concept with a theory. I don't know if that made any sense, but here's an example. Alfred Wegener's concept of continental drift. Actually, a lot of people had come up with this before. He's just the first one to really put it on paper. And his major failings were that he didn't provide any mechanisms for this drift. And so it remained a hypothesis. And it did not become the theory of plate tectonics. Plate tectonics is different than continental drift. Continental drift has been abandoned because Wegener in his concept just kind of thought the continents floated about on the ocean floor, which at the time most people still thought was featureless and level. Plate tectonics, when we started getting pictures of the ocean floor, we needed something different to explain it. Yes, his core concept was correct. The continents move about the globe over time. But after that, it breaks down. So something else has replaced it. And that's the theory of plate tectonics. So over time, theories can be falsified, just like hypotheses can be falsified because they're explanations. But theories are well-established things. And that's why we usually just work within them, because like if I'm trying to reclassify the stratigraphy of a geologic unit, there is nothing in that narrow redefinition that I'm trying to do for that unit that is going to sit there and nullify any geologic theories that are out there. It's just not going to happen. So I'm working within well-established principles of geology. Okay, so that's why that's just a basic example of why most of us work within theories or groups of theories, and I hope that's clear. Okay, so to recap here, number one, I hope my explanation has been beneficial. Rely more on the definitions if you wish. Please feel free to comment below, or if I didn't elaborate or I confused you, feel free to ask for more explanation. But I'm going to do a recap here. So initially in the scientific method, what you're doing is you're making an observation or you're formulating a question. Either your observation will lead to a question, your question will lead to an observation, vice versa, it doesn't matter. And then you start to formulate a hypothesis, a concept, but something that's testable, something that describes the natural world that can be tested. So then you run your experiments or you make more observations, and you either find your hypothesis has been falsified, you're totally wrong, experiments don't match any of your idea, doesn't match your idea at all. It's kind of correct, like the experiment was leading us there, and it's like, okay, this could possibly still be fine, but the way I've worded it is incorrect, or I need to expand on it, or I need to extrapolate something, so you redefine your hypothesis. Or all your experimental data support your hypothesis and you can move on. Now, I'm here to tell you that last part almost never happens from the get-go. It's usually a lot of falsification and usually a lot of refinement in the process, and a lot of, what did I do wrong? Because a good scientist always doesn't think, Eureka, I got it right. A good scientist thinks, how did I get that wrong? Or did I miss something? Or this is too good to be true. Where did I screw up? That's very important. So, and then you take the data, essentially, that you've collected from your experiments, and you analyze it and you form a conclusion. So, and like I said before, I would like to see falsified conclusions published as much as supported conclusions, but that rarely happens. And then from that point, you may be done. You may not be able to go any further, or so you can start over from a different perspective, or from a different question, or from a different observation, and start the process all over again. But if it's new ground, you can ask further questions and expand upon it, and eventually you can, if things work out, you may end up with a totally new scientific theory. But like I said, that doesn't usually happen. And like I stated in the beginning, there are slight variations to this. I was just dealing with the natural sciences, if you will. I use that explanation. But this core here is a good standard to work by, and it is pretty solid. I mean, like I said, it can move a little bit, but that's a good start to finish, if you will. Even though, you know, if your hypothesis turns out to be incorrect, you got to go back to the drawing board, start over again, or you just may abandon it there and realize it's pointless and move on to something else. You know, but that's generally so it's not just a rigid thing. It adapts and changes depending on its usage, and I hope you understand that as well. But anyway, that's it. I hope you learned something, and I guess I'll see you when I see you.